Geology in a Nutshell, Alyssa Smith with news and research, and Portland Basin Geology with Paul Edison-Lahm. Welcome to the GSOC Geology Hour. I'm Carrie Gordon.
And I'm Alyssa Smith.
And I'm Paul Edison-Lahm.
And now, over to Alyssa.
So this is my little segment I've been calling Geology in a Nutshell, where my goal is to go through and summarize a few different research articles that have come out as of late. So today we're going to be looking at the pyramids of Egypt and copper contamination, a geological view of a binary asteroid system, and the longest ever drill core of Earth's mantle. So this first article is called The Construction of the Giza Pyramids Chronicled by Human Copper Contamination. So this study is a chemical study of some ancient metalworking activities that happened in the Khufu harbor. So this is obviously an artist rendering here that shows the location of Khufu Harbor, which is a now defunct branch of the Nile. And it was the site of extensive copper working really early in Egyptian history. So this map shows here the locations of a few different things, including the defunct branch of the Nile. So this is where that would have been at the time in relation to the pyramids. And so the place where they took a sample was right here. They did a coring, a sediment core. So here is an image of the researchers taking the actual sample. And something I always think is very interesting is we don't realize that the pyramids are in, close to current civilization as well. So this kind of gives you that perspective. So this is an image from a different study in the same area that shows some of the tools that may have been created around then. Well, this is what they look like now anyway. So these were mostly copper tools used for working limestone, wood, textiles, things like that. And the importance here is that they sometimes were alloyed with things like arsenic for added durability. So it's always something we worry about is arsenic, just another contaminant they can measure. So all in all, they measured copper and arsenic, as I mentioned, as well as aluminum, iron, and titanium in their core sample. And then they also were able to take 6 new carbon-14 dates to try and establish a chronology of what they were, this copper pollution they were looking at. And so this is a graphic from the study itself. And so what we've got here is, so this is the evolution of copper contamination in relation to historical periods. So on the y-axis here, we have the measure for copper contamination. And so they used some statistical analyses to be able to represent this here. And then on the bottom here, the x-axis, we have the historical periods. So the timing, as far as things go, the younger dates, so closer to where we are now, is on the left-hand side of the graph, and the older dates are on the right-hand side. So they use these new calibrated carbon-14 ages for these older periods, the pre-dynastic through the Old Kingdom timing here. What this study found, why this was so important, is that they found that there was an uptick in like the ambient copper in the sediments prior to any sorts of construction of large monuments in the area. So this is about 200 years earlier than previous estimates. And what that's associated with is early settlements in this area. So like I said, before they started the big construction events, which is kind of what we all think about when we think of ancient Egypt. So there was another uptick in the copper in the soils that they know is associated with some early construction efforts, mostly tombs of high-ranking officials. And then the highest levels of copper in these soils are associated with the construction of the pyramids and the Great Sphinx. And the geochemists, the expert geochemists that they quoted in this article, mentioned that this study is extremely well done. It's just very high level work. And the importance in it lies between this potential use of us linking geochemistry to the lives of everyday ancient Egyptians, because a lot of the emphasis goes to these big monuments, to what would have been considered quote unquote important people. And there's not enough there's really not enough views of the everyday people who were around then. And I really liked this quote from the article that said, "The sediments are as important as monuments."
I'm curious, where did the copper come from? Was it being traded into Egypt from the east, or was it found upstream on the Nile?
This is Matt. Can I offer some
Please.
insight?
Please.
Before tin became the main alloy of copper to make bronze, it was made with arsenic and antimony. And
Oh,
so this is a very early form of bronze. And as far as copper uh, mining was concerned, the whole island of Cyprus. I mean, Cyprus means copper, or copper means Cyprus, or something like that. So there
oh,
was there was a whole lot of it around. So when tin made the best bronze, but it came along a little bit. Tin smelting for bronze came along a little bit later, but arsenic was one of the earliest forms of making copper better.
Hi, this is Neil Olson. The I believe the Latin name for the name Cyprus comes from the Latin for cuprum, cuprum, and that now comes down to why copper has the Cu as the letters for the elements.
I did see that someone asked whether copper was, what was it, used as a mordant. Did that
No,
get
Paul, I
answered?
know copper was used as a mordant
Okay.
because uh, a family member has used it, and you could take copper pennies and drop it into your dye bath, and it will alter the color of the fiber, which that was it's like, oh, wait a minute, if they had copper in Egypt, and that could explain some of the really amazing color hues that show up in the fabrics and the textiles and the rugs. Because it's like, well, copper alters natural dyes to different different tones. So it's metals come into play besides ending up being tools or jewelry.
cool. So we're going to do a hard pivot and we're going to leave ancient Egypt and we're going to go into outer space. This summary title is A Binary Asteroid System Gets Its Geological Close-Up. So this is an image here of the Didymos binary system. And binary system infers that there's two different asteroids there. So this system was focus of the NASA's DART mission, which is the Double Asteroid Redirection Test. So what happened is they had a 500 some kilogram impactor that the plan was to have this impact one of the asteroids in the system to first off, see if there's any potential to affect orbits, but also to be able to study these asteroids. And what was really neat is they saw that the orbit of Dimorphos, which is one of these two asteroids, was significantly affected by the impact. So what that shows is that there's actually a chance, in the future, that if they're looking into seeing whether or not we can change the trajectories of asteroids and things coming from outer space that might be on a near Earth trajectory, there's at least some chance that we might be able to do something about it. So that's pretty interesting in itself. I'm not saying the technology is there yet. It's not, but there's a chance. So this is an image from NASA of, I believe it's a SpaceX capsule that was delivering the equipment there. And so really neat. So this started about 2 years ago. Asteroids themselves are really important tools for studying the solar system. There's people who do work on meteorites, as we're all very aware. But the thing is that with meteorites, it's a really tough journey getting from outer space to Earth's surface. And those meteorites are going to be very heavily altered by, all the steps along the way from those meteors being created to entering the Earth's system to being deposited on the Earth's surface. And even once they're here, if they sit there for a while, then the surface is also not kind to them. So ideally, we would want to be able to visit these asteroids and sample them directly, but oftentimes that's not the case. But the thing is that with this mission, they were able to take a lot of imagery from these asteroids and at a much higher resolution than any Earth-based telescopes, but also better than anything else that we have that is currently in space. So geologists were then able to use these images to create a much more higher resolution perspective of asteroid surfaces. So really, really neat thing. And this image, as the caption says here, is the last image of Didymos before impact. So these are some of the images that were generated by this study. And there were a few more in the paper, and I just want to highlight the ones I thought were the most interesting. So the one on the left shows the geologic units. So they broke it down into 3 different types. So you've got the smooth lowland, which is the middle area that's in yellow, the transition region, which is just on the periphery there in green, and then the rough highland, which is on the edges of our image from this view in the purple. So this is something they couldn't have done with Earth-based or space-based resources just based on resolution. But then they were also able to look at the shape and elevation of it. So on the right-hand side is a color, like a temperature color based, not the temperature, I mean the color scale based image showing the differences in elevation there. These are images of the surfaces of Dimorphos, which is in the purple, and then a few other asteroids that have had missions where they took imagery of the surface. And these colors are not the actual colors. These are false colors. It would be really neat if that's what they look like, but they don't. So it's just a color key to show these are the ones that they looked at in more detail. And of the 2 different colors, it's the blue ones that the scientists were really focused on. And so the scale bars in the corner of each of the images give you a sense of how large these are. So we're zooming in a little bit more. There's really high resolution pictures. So these boulders are really large, even for the size of the asteroid itself. And I want to mention that the article goes back and forth between saying Didymos and Dimorphos, but they're the same system. So the importance of this image is so we see the size of the boulders here. There's a lot of variation in the particle size on these 2 asteroids. And the largest on either of these is about 160 meters across, which, that's a pretty sizable thing. But when you put it in perspective, the largest boulders that are on these asteroids are about 20% of the total diameter of Didymos. And to put that into even more perspective, Mount Everest, the tallest mountain on Earth, if you were measuring it from sea level to summit, would only be about 0.1% of Earth's diameter. So wild. I can't even fathom that personally. So the significance here is that, so these are 2 images showing the size distributions. So the blue are the smaller boulders, orange is slightly larger, green slightly larger than that, and red slightly larger than that. Which, if you're not relying on the colors here, just thinking accessibility reasons, the largest bars are going to be the smallest boulders. And in a lot of these, you increase, as the size increases, there's less of them, but not in all of them. So just kind of an interesting thing. But what they call these are rubble piles. And what the scientists on this paper described this as is that essentially you have a bunch of boulders of varying sizes that are so very loosely held together by gravity. So one of the thoughts as they were looking at this system is that Dimorphos, the smaller of the 2 bodies, may actually be that all of that material was sourced from Didymos initially, and that there was now it's kind of very, very loosely held together as its own body And that's kind of what they're looking at. There's several other studies on this. And also, if you want to take a look at the paper itself, it goes a lot more into the morphology of these asteroids, the physical nature. Really good article, really interesting sort of developments there. So the last piece is a really, really fascinating one, in my opinion. And if you're looking for articles that spin into other articles and then so on and so forth. So this summary article is actually, this one's from Live Science in August of this year. And essentially the full title, it's Science's real largest ever piece of Earth's mantle. This is an image in the background of a piece of this mantle that was brought up. So this is an image of some of the scientists looking at a piece of this core. So this was an over 1,200 meter long sample of peridotite from the Atlantis Massif. So that is in the Atlantic Ocean near the mid-ocean ridge in an area called the Lost City Vent Field. So if you take a look at this article, I was like, okay, maybe I shouldn't look at this one. It sounds a little clickbaity because it's like, okay, it comes from Lost City. I always thought it was, maybe getting into the pop science kind of realm. But no, that's what the vent field is called. So really interesting area. And these were taken by drills off of a ship, a research ship that's been out there. And it's a really huge project. Unfortunately, is coming to an end. But this is the deepest sample that's been taken from ocean drilling efforts to date. And it's really significant in that regards. And this piece of upper mantle material is giving scientists the opportunity to look at structural and mineralogical features of the mantle that are really, really hard to observe otherwise. So if we were to look at the mantle is largely made up of peridotite. So this is a fresh piece of peridotite. And this specific type is called Hartsbergite, which if you know much about different types of mantle, it's pretty significant in itself, but I'll get into that. But it's mostly olivine and pyroxene minerals. And these are minerals that don't play well with water, and they don't do well at the surface or, near the surface. They're meant to be at high temperatures and pressures. If we were to look at this under a geological microscope, cross-polar, we would see something like this. So if you're looking at this, the kind of gray and kind of brownish crystals are probably pyroxene, mostly orthopyroxene, and the brighter colored, really heavily fractured stuff is olivine. So one of the things is like I said, it doesn't do well with water or anything like that. It doesn't fit in the chemical structure. And so what's happening at this place is that there's actually tectonically exposed mantle bits in this location that are being exposed to relatively cold carbonate-rich fluids, which then serpentinizes the material or transforms it from mostly olivine and pyroxene to having a larger percent of serpentine. So what that looks like, if we were taking the same kind of a view as the image on the left, it kind of turns into this mottled kind of a mess, and that kind of fuzzy gray stuff is serpentine. So it's something that we would expect to happen in these systems because, you're pulling apart the crust and you've got, mantle in this area being exposed and water getting in there. So it's going to mess things up. But this is something where they can, instead of just saying, yeah, we know this should happen, they can actually look at it. So really, really significant. I seriously can't get on how cool this is. One of the things is ideally, if we were trying to study the mantle, we would want to see the really fresh stuff, but that's not what we get. So what the author of this said is, extracting information about the mantle from serpentinized peridotites is like reading your child's school report after it somehow fell into a puddle of water. The grades can be deciphered, but details in the accompanying teacher's note are illegible. So I really, really liked that. So regardless of saying, hey, this isn't an ideal situation, they could still get a lot out of this. So what they found is that about 40% of these cores have been serpentinized. And also, they know because of the type of peridotite rock that they have, in order to generate Hart-Spaghetic peridotite, you have to have a really high degree of melt to deplete the mantle that much. But the question is how do these melts actually physically leave the mantle? So the mantle is a messy, messy place. So let me pull a diagram here. So what we did, I put a brown bracket around the crust here. The images are all kind of the same color. So we've got the crust on top, we've got some fault shown there, and then underneath you've got a stiffer layer of peridotite, and then below there is softer, and then you've got solid flow that happens. So this box that I highlighted in green here is the part that's blown up on the side. And you see you've got the kind of lighter color and then the darker colored little blebs in there. And those are refractory bits. So refractory materials are going to be things that are require a higher temperature to melt. So that's going to be significant. So when they're trying to think of how these melts could have actually got out of the system, one of the options is that there was the development of these kind of melt channels in the peridotite below, and that through these channels they were able to, or not they were able to, but the mantle was able to extract and transport melts all the way up to the base of the crust. And if this were the case, what they should see is these channelized kind of interconnected networks of what would be left behind, which is dunite. Now, dunite is a type of peridotite that's even more depleted than Hart-Spaghetic, and essentially it's almost entirely all olivine. So they should see that if that's the case. And it's a really hard thing to observe and kind of even to explain, but having this core is really helpful. What they found is that they do see these interconnected dunite channels. But the question is, are these actually recent materials? Like, are these refractory materials and then these channels kind of like the same age and recent? So there's other evidence that's been gathered, mostly radiogenic isotopes, that say this refractory material looks like it's really old. So the second option is that these Hart-Spaghetic are not melting. They're too refractory. It would take too high a temperature to be able to melt these bits. So instead, what's happening is there's a younger melt that's passing through this older material instead, and that's how these melts are escaping the mantle. So the next steps that they proposed are going to be looking at some very specific radiogenic isotopes, so osmium, neodymium, and hafnium, to look at the time scales here and see if there's any way that they can deduce whether or not this Hart-Spaghetic refractory components are old or if they are more recent. But as I kind of mentioned earlier, it seems like the funding for those missions is kind of running out. So I'm hoping to see more from this. Maybe, I guess, if enough of us get excited, we'll just start sending more and more ships out into the ocean to take pieces of the mantle because we're interested in it.
All right, Paul, can you take us into the Portland Basin geology?
Sure. Welcome everyone. This is Portland Basin Geology. We have some just amazing geology in the Pacific Northwest generally that we get to on many of our GSOC field trips. And we've been up to the channeled scablands, Columbia Gorge and Columbia River basalts, Mount Hood and the Cascades, and of course moonscapes like the Blue Basin. But you'll notice a lot of those field trips are on the east side of that dotted line, which marks the Cascades, and where it's drier. Whereas those of us who live here in Portland and the Willamette Valley, as many of us do, where it rains, all of that wonderful geology is covered up by these things, trees and grass and buildings and so forth. So this talk is entitled Geology of the Portland Basin and How to Find It, drawing in large part from the field trips that we've put together with GSOC in the past decade. I'm going to tell the geologic story, which many of you know, sing along, kind of keep this in chronological order and then look for places where it actually outcrops in Portland Basin, or you can see some evidence of it. As you may remember, back in the Jurassic Oregon, there was no land here at all. It was just ocean crust, ichthyosaurs and plesiosaurs and other small dying creatures. All the activity was going on the other side of the planet, where the supercontinent Pangaea was breaking up, sending the North American continent hurtling toward us at 1 inch a year. And that leads us to the main character in our story, which is the story of subduction, which is when that ocean crust encounters the continent overrides it, and the crust is forced down like a conveyor belt, really carrying with it anything that's on the ocean floor, whether it be sand or clay or fish bones or tin cans or even islands, as in the case of the Silesia Island arc, which we believe was the first land to arrive at the North American continent, where docking about 50 million years ago. And now we understand that that Silesia was actually an expression of the Yellowstone hotspot, which at that point was where it is pretty much now, but the continent hadn't yet reached it. It hadn't traveled over it in its path westward. So looking at the Portland Basin, it's this little area here up in the northwest of Oregon. I'm going to overlay a geologic map. And here, this is a map of the Silesia terrain once it's docked. The red parts are places where the Silesia outcrops, like Mary's Peak, and the pink parts are where it's presumed to be underneath. So if we look at the Portland Basin, if we go down deep enough, that would be our basement layer of Silesia basalt. It doesn't outcrop anywhere in the basin, but what we do have is something that happened a little later, the Waverly basalts, which erupted about 38 million years ago when the continent had passed over the Yellowstone hotspot. So these eruptions are interior, and those do outcrop. If we zoom in from Portland to the city of Milwaukee to the south here, and then look at a geologic map, this which is very colorful. I'm going to make it a little simpler. This gray chunk there is the Waverly basalt that outcrops at that bend in the Willamette River where Johnson Creek intersects and has the confluence there. So it does outcrop right there on the bike path at 17th Avenue and Highway 224. There's the intrepid Sheila Alson doing a recon for what it turned out to be our East Side bike trip that we do every year. These are the Waverly basalts, and they're really crumbly. It's really great to get to these basalts because you can break them open sometimes with your hand or just on the ground, and they contain these really cool zeolite crystals because the water percolates through the rock and then precipitates the silica into the vugs in the very old basalt. So that's the oldest rock. Well, that's the oldest native rock, we would say. I guess if you really want old rocks, come on the Building Stone tour. We've got another one coming up on October 13th, and you've got stuff like the Morton Gneiss here, which is billions of years old. We've learned from Ray Wells and others that the entire Pacific Northwest, Oregon and Washington is rotating at the frantic pace of 1 degree every million years. And this results in some shear zones that open up as pull-apart basins, or rhombochasms as they're called. And the Portland Basin is, in fact, exactly one of these rhombochasms, one of these pull-apart basins. The basin itself is about 50 miles long, about 20 miles across, trending roughly north-northwest, south-southeast. And you think of many basins and valleys as being carved by the rivers within them. But in this case, the tectonic basin, the Portland Basin, has essentially captured the Columbia and Willamette within. Geologist Eden Main compares it more to a chafing dish. I had to look up what a chafing dish is, but it's a shallow basin. So you usually don't think of our geology or geography in terms of the Portland Basin, but this is really where most of the metro area is, including Vancouver and Clark County and Multnomah County. It is extensional topography. It's being pulled apart, and that results in these Horst and Graben forms, where the Graben, which is German for grave, drops down and the horse is the raised up portion. If you look to the east from the west side of Portland, you see all these bumps. And looking at the geologic map, these are the buttes, the east side buttes. If you look at a geologic map, again, lots of colors, but I'm going to make it simpler. Those bumps are all surrounded by normal faults. And so they're essentially, in various forms, horse. But not only are they horse, they are also capped by or accompanied by volcanics. So most of them are either monogenetic cinder cones that happen once, or in some cases, shield volcanoes that have multiple eruptions. We call these the boring volcanics after the town of Boring. They're anything but. Now you notice in the background, there's Mount Hood. That's where subduction volcanics are supposed to be erupting. And back there on that, as we'll talk about in a moment, we're a little puzzled why we're getting volcanics erupting to the west of the Cascades. And that's a geologic mystery that I'll come back to in a moment. We're still in this period of volcanism. For the past 2.6 million years, we've had about 60 or 70 of these volcanoes erupt in the Portland area, the most recent being Beacon Rock out in the gorge 58,000 years ago. So we can expect another one of these to pop up in the Portland metro area at some point. Dr. Paul Hammond penned an article a few years ago that we actually thought was kind of inflammatory because it did discuss what would happen if one of these popped up in the middle of the Portland metro area, kind of how that would proceed. That's Mount Tabor, and it's not going to erupt again. It erupted 200,000 years ago, and again, it's a monogenetic volcano. It only happens once. So you don't have to worry about that. You got plenty of things to worry about, so don't worry about boring volcanics coming up in your backyard. But we do get out to Mount Tabor periodically, and on our Boring Buttes trip, for example, and I'm doing a piece with the Urban Nature series about once every month. And we get out there and look at the cinder cone that we have a special connection to, because were it not for us, the local gardeners and the Parks Department would have continued to mine out that cinder cone. The reason it's exposed like this is it was mined for ornamental gravels, for path gravels, and so forth. But GSOC had a significant role with the Park Service in preserving what is up there, which was at the time referred to as Cinderella. Moreover, we've had a recent Vogt scholar, Darlene Verduzco, doing her master's work out there, and there she is collecting scoria with Dr. Vanessa Swenton. And then she took that scoria and very painstakingly went through with tweezers and plucked out the olivine crystals in there. And then with those olivine crystals, looked for gas bubbles in the olivine crystals. And then through some geomagic is figuring out how quickly that means the magma came up. And I think she's still waiting for results from the lab there. But the general theory now, I believe, and Matt may correct me on this if there's something newer that we know, is that the normal faults, this extensional topography created some kind of plumbing system so that we've got volcanics coming up in the Forearc Basin to the west of the Cascades, which is to the west of where we would normally expect it. One of the things I love about the buttes is that many of them, though we think of them as volcanoes, they're capped with river rock, which is in the blue in that diagram there. So that you can go up to the top of Mount Tabor or Powell Butte and you can see river rock from the Columbia or river rock that was brought down from the Cascades. And sometimes you can even find entrained in the magma, or entrained in the lava, I should say, river rock. This is an andesite that was entrained in the lava on the northwest side of Powell Butte. So the next feature of subduction, of course, one of the most prominent, is that as that ocean crust gets down about 60 miles or so, it releases the water in it. The water rises as heat rises, and it causes melting in the rock above, which rises as heat rises and creates volcanoes. So the entire Cascade Range is basically the surface expression of where the Juan de Fuca plate gets down to 60 miles or so and creates a chain of volcanoes above it. There's only one river that crosses it, or one major river that crosses it. Chihuahua or Wimhall, a super highway for civilizations since time immemorial, or at least the past 10 or 20,000 years. The Columbia River crosses the Cascades. And cool geologic fact, When you have a river that crosses a mountain range in its entirety, it means that the river was there first, and the mountain range came up underneath, and the river obligingly cut down into it, creating our Columbia Gorge. So there's been a river draining Montana and Canada and Idaho and Utah and so forth for tens of millions of years, but the Cascades have only been in that position for a few million years. And that's where we get our Columbia Gorge. It's the river, the Columbia cut through the gorge, which is central to our story in the Portland Basin because it's been the source of two catastrophic floods. One of rock and ice that you probably know about, the Missoula floods that came in from the east during the Ice Age and flooded the Willamette Valley. Another one that people are less aware of often, which is the Columbia River basalts, which also flowed from the east all the way to the coast. Let's start with that. That's the Columbia River basalts about 17, 16 million years ago, started from giant fissures that opened up in eastern Oregon and Washington that were yards wide and miles long, or perhaps meters wide and kilometers long, no one knows for sure. But here represented by the blue, the spreading blue stuff. I mean, imagine the rivers of lava that you saw in Hawaii in 2018, filling the entire watershed, and where it can penetrate the Cascades to the west, it flows through the lowland created by the Columbia River and covers up the Silesia block that we've already discussed. So now we've got two layers. We've got the Silesia block of basalts, and then we've got the Columbia River basalts on top of that. So it's sort of like this. I mean, there's Silesia down below and then Columbia River basalts. Those are the West Hills. So we can see them very clearly in the West Hills, which is an anticline of CRB and Columbia River basalt that's upthrust. And on one of our field trips, this is our Portland by tram, train, and foot trip. There's Sheila again, looking at some winter water formation of the Columbia River basalts. And you see how they form those nice columns that when you've got a flow of basalt, the basalt cracks perpendicular to the cooling surface, and you get these wonderful hexagonal columns that you see everywhere around town in ornamental forms and so forth, people's gardens. But you're more likely to see the basalts just in the ordinary basalt cobbles that are pretty much everywhere around town. And these humble gray rocks that are, I guess, a mixture of olivine and pyroxene, and then there's a sort of spray of feldspar, the white in there. Pretty common for those of us in Oregon, exotic for other places in the world, but we're happy to be the home of so many basalts, both Silesia and Columbia Gorge and boring basalts. The gorge itself has been bringing rocks down for millions of years, and in the last 2 or 3 million years, we have a formation we call the Troutdale Formation, named after the town of Troutdale. And all of those rocks that have been brought down from Canada, from Idaho, from Washington, can be found in this particular spot. This is again from our bike tour, which Ian Maiden led. Near the Steel Bridge, this rock, it's so indurated, it's so hard that this is one of the only places on the Willamette River in town that doesn't need any riprap. That rock is so resistant to erosion. So that would be the next layer if we wanted to do this chronologically. Now that diagram is a terrible oversimplification because what you have is the river kind of wending back and forth over time, leaving silt and clay, leaving sand, leaving gravels, and kind of moving back and forth. And so the real picture is much more complex than this, but essentially that's the sort of next layer in our story. And the layer after that, of course, is the Missoula flood layer. Again, most of you know this story, so you join me in singing along. During the last ice age, when the United States was invaded by these giant ice sheets from Canada, what is now Flathead Lake up there in Missoula the drainages were blocked and became Glacial Lake Missoula over there on the right of the screen, which was blocked by an ice dam, which periodically broke, and all of that water flooded out in hours or days, carving out the channeled scablands and past those terrifying JPEG artifacts in my diagram and through the Wallula Gap, and again through the lowland and the gorge created by the Columbia River, into the Willamette Valley, where it sloshed around and then eventually drained out to the ocean. So it flooded into the Portland Basin at 60 miles an hour and covered us up here to a height and altitude of 400 feet. It might have looked like this if you were here, or if someone had Photoshop back then. But we actually know from the work of Dr. David Lewis and others that there are Calapoola stories that are eyewitness to the flood. And so we think there might have been people up on those buttes, terrified and wet, and hopefully figuring out a way to escape at the time, at the end of the Ice Age. Geologically, what happened in the basin is that as the water came in very fast, it has more area to move into, and so the velocity decreases as it slows. It drops its first load of gravels. And so that's what we see in the east side of Portland and Vancouver. This is from a quarry trip we took back in 2017. The water pushes on these cross-bedded gravels that are very, very resistant to erosion. And in fact, on our Johnson Creek trip, we've got a great outcrop that Matt and Melanie Klim found. I guess this is about 75th Avenue up there. And you can see that the river has carved in to those gravels it's a very steep cliff on the outer banks of the river there. When the water had a chance to calm and slow and create this, what we call temporary Lake Allison, as it drained out slowly, it left behind layers of sand and silt. And this leaves a different sort of deposit. Imagine, for example, the water rushing in, and this is not a completely accurate map, but just a general model. The waters come in and the heavier gravels drop out first, sort of a gradient to the east. And then the fine sediments settle. And then this happened apparently 40 times. So we have all of those layers, and then an additional 12, 15,000 years of people living here or development and so forth, and erosion. What gets left behind are these rhythmites. So, and this is the work of David James in his master's thesis from Portland State. First, the smaller gravels drop out, and then we get the sands and silts. Maybe there's an interval between floods, maybe a smaller flood, another pulse of gravel there, and then maybe more sands and silts and so on. And this is how we know, by counting the rhythmites, that we've had 40 floods here. The problem as far as field trips is that these are very soft, and so they erode quickly whenever they appear. We do have one on the bike trip that Jim O'Connor identified a few years ago after a landslide near Ross Island Sand and Gravel. You can sort of tell that you have to kind of use your imagination, but that's an area that was mapped as a rhythmite. But it's easier to find evidence of the Missoula floods in, again, the gravels and cobbles that you see around town, especially those orange rocks that are the distinctive quartzites. These are metamorphic rocks. And as I mentioned, Portland doesn't have really old rocks here. This one was once a beach. It was once sand that got covered up and metamorphosed and then eroded out. And it's probably about 1.5 billion years old, or 1.4 billion years old from the Montana Fold Belt up in Idaho. So it would have come down through the Columbia River. By the way, if you're curious about our name, the Geological Society of the Oregon Country, it was chosen by our founder, Dr. E.T. Hodge, to roughly correspond to the drainages of the Snake and Columbia rivers. Of course, it's a colonial concept. If we went back to our pre-1846 borders, we could march up to Vancouver, BC, and claim our membership up there. But again, you'll see the evidence of the floods in any pavement, any sidewalk in Portland. You'll see a mixture of basalts and quartzites, and a few exotic gravel, granites, for example, or Chalice volcanics from Idaho. Finally, one of the most important consequences of subduction is that conveyor belt gets stuck and occasionally releases in an earthquake. And this is a story that many of you know that starts with our understanding of the Native American stories of Thunderbird and Whale, confirmed in part by the ghost forests at the coast that reveal that those trees were all all died in the same year when the land dropped and the trees were inundated by sand from a tsunami and died in the following season. But the real smoking gun, of course, is the Japanese orphan tsunami. The Japanese keep very careful records of tsunamis, which are almost always associated with earthquakes within 15 minutes or so. But in 1700, there was one that occurred without an earthquake. And so going backward, judging that a tsunami travels across the ocean at about the speed of a jet plane, scientists have figured out that the last Cascadia quake was January 26, 1700 at 9 p.m. I think the 9 p.m. is really just geologists showing off, but in any event, the work of Chris Goldfinger and Brian Atwater and others indicate that in the past 10,000 years, we've had magnitude 8 or magnitude 9 about every 300 years. And the last one was 300 years ago. So as some would say, we're about 9.5 months pregnant for the next earthquake. This is important in the basin. If you live in the gravels or on the buttes, you're in pretty good shape. I'm going to overlay a hazard map from the State Department of Geology and Mineral Industries. And it's pretty much what you'd think. The lighter areas are good, better places to be on those gravels or the buttes. And the orange places are less good. If you're in the fine sediments there, I guess in part it depends upon how deep the water table is. If you have water mixed with the fine sediments, you're more likely to have the liquefaction. So the worst place to be is down by the river. Yeah, there it is. At the beginning of the 20th century, the river was dredged and the surrounding floodplain was filled with material to create room for the industry down there. And that is unfortunately where we have our critical energy infrastructure in the red zone. And that is where 95% of the fossil fuels in Oregon pass through. And unfortunately, the ground under there is subject to liquefaction. In a Cascadia quake, the ground will liquefy, the tanks will fail, catch fire, releasing toxic fumes, and then float downriver, causing environmental catastrophe. So that's one of our biggest concerns, and we can't take credit for this person, Yumei Wang, an engineer with the Department of Geology and Mineral Industries, although she is a member of GSOC and she's been pretty influential. But it was her work in 2013 and the work of others that really brought the critical energy infrastructure to light and has resulted in subsequent legislation and attention from the New Yorker and media and so on. We can take credit, and I think we should, for the work that GSOC did under the presidencies of President Alson and Neuendorp to protect the Department of Geology and Mineral Industries, both from the budget acts and also from the executive and legislative acts to get rid of the agency a few years ago. And we lobbied for that. We're a small volunteer organization, so we're not really in a position to take any divisive political positions, but I'm proud that we stepped forward on that and also lobbied too on Senate Bill 1567, which was the bill that passed that gives the Department of Environmental Quality, finally, regulatory authority over the tanks and requires the fossil fuel companies to create seismic risk mitigation programs. So for the first time now, we have a better estimate of the risk and we have some path going forward. But I would encourage people to stay curious about that because there's probably more action that will be needed to take in the future. So I am 1.5 minutes away from our hour. And just to quickly wrap up, but with the GSOC field trips that are coming up, because we have many that are local, and the end of our field trip season is about now, is about in the coming month, but we'll be starting up again in the spring. Now I looked last night at the website. I see that we've got a landslide strip coming up. That's probably a Scott Burns strip because Scott's our landslides guy, but no spaces left. So you got to jump on these sometimes when they happen. Now, you don't have to be a GSOC member to attend our lectures or our rock show and tell. You do have to be a member to attend these field trips, and that's one of the purposes and the benefits of membership. There is another trip coming up, as I mentioned, and that's my downtown Portland Building Stone tour that GSOC has been doing in one form or another since the 1950s, but we really revived it about 10 years ago. And as of last night, I don't know, I haven't checked this morning, but we still had 3 spaces left. So join us on that. If you really want to see the oldest rocks in the Portland Basin, they're all downtown. And with that, I will conclude and thank you. And if you're interested, there's certainly more to be found at our website, gsoc.org.